Welcome back, students. In this section of the class, we are going to take a little bit of a turn and talk for a few lectures about molecular symmetry. So in the last few lectures, we have been combining atomic orbitals into molecular orbitals, and we've kind of been loosely referring to symmetry. This works pretty easily when we were talking about two atoms. We could talk about overlap between the orbitals and so forth. But we started doing things like combining more atoms into molecules. So we did things with water, we looked at formaldehyde, and it got more complicated here when we use these more complicated molecules. So here we want to take a little bit to look at what we mean when we say symmetry. So what we're going to do is first introduce the idea of symmetry in point groups. And then we're going to talk about how we can use this mathematically to construct molecular orbitals. And finally, we'll talk about the vibrational modes to see which modes are symmetric and therefore IR inactive, and which ones are not symmetric and therefore IR active. So the learning goals for today are going to be to determine the symmetry operators for a molecule. So in which ways are certain molecules symmetric? Then using that information, we're also going to want to assign molecules to their point groups. For those of you who have taken inorganic chemistry, we're not going to do this in as extreme form as you do there. We're going to stick with the simpler point groups for this class. And then we're going to apply symmetry operations, and we're going to determine the matrix forms of the symmetry operator. So actually what happens to the molecule when you operate on it with these symmetry operators. And we're going to turn that into matrix form. We'll see how that's done towards the end of the lecture today. So to start, we are going to look at the water molecule. So here is a representation of the water molecule. And I want you guys to pause the video here and determine the ways in which this water molecule is symmetric. All right, so hopefully you had a chance to determine how this water molecule is symmetric, and now we're going to talk about it. So one way this molecule is symmetric is that we can draw a mirror plane right through this molecule here. So if we cut this molecule in half, we can reflect across this mirror plane and make this molecule the same, right? If we reflect across this plane, it's symmetric in that way. Another way we could do it is we could have a second mirror plane that's actually in the plane of the screen here. So we could bisect all of the atoms and it would be symmetric on either side. We have one more thing that we could do to make this symmetric, and we could physically rotate this molecule. So if we took this hydrogen, rotated it all the way over here, we would have a symmetric molecule. We wouldn't have changed the appearance of the molecule. So these three operations are the three symmetry operations for this water molecule. There's one more operation, and that is the identity operator, which means if we do nothing to the molecule. And that's important for developing group theory, and we'll see that as well. So this kind of symmetry, we can talk about it, and it actually turns out to be pretty important for these molecules. So remember, back to a couple lectures ago, we talked about the difference between water and beryllium hydride. And we found that beryllium hydride was this linear molecule. If water was linear, if it had a different kind of symmetry, it wouldn't be a polar molecule and it wouldn't stick together with forming tight hydrogen bonds like it does because of the dipole. And then it wouldn't have the same properties that we know water to have. So compare, water molecules to carbon dioxide, which are linear molecules with polar bonds. That is a gas. So the shape of the molecule, and we can describe that shape with the symmetry, is actually imperative for the molecule's function. So now let's take a look at the other types of symmetry operators that we could have. So the types of symmetry elements that we can have are as follows. So they're all geometric elements. We can have axes, so we can have lines that go through these. We can have certain points, and we can have planes. So we saw in the last one for water, we had a rotation axis rotating along this axis here, and we also had two mirror planes. Now, when we're doing symmetry on these molecules, we're doing something to them to make the molecules unchanged. And if they are unchanged after doing some sort of mirror reflection or rotation or so forth, we have a symmetric molecule, and we have a symmetry operator that goes along with it. So the 5 types of symmetry operators that we have are as follows. We have the E, which is the identity operator, which just means doing nothing to the molecule. We have a C sub n. So these C sub n operations are rotation axes. So for water, it's a C2 rotation axis because we rotate it twice to get back to the starting point. We rotate it by 180 degrees. We can also have sigmas, which are mirror planes that talk about being reflected through the mirror planes and different planes that we set up. So we set that for the water molecule. We can have, so these are the pretty easy ones. Now, these ones down here are a little bit more complicated. So we can have inversion centers, which have the symmetry operator of I. And then this is taking every point. So if we take the point x, y, z and make it the point negative x, negative y, negative z, so putting it through, you know, all the way to the other side. If that leaves the molecule unchanged, that's an inversion center, and that's a point. And you can also have these funky ones here, these S sub n's, which are n-fold rotation and reflection axes. And we'll talk about these a little bit more in class. We'll bring in some models and play around with them and kind of see the sorts of things that we can do. So before class, if you would, have a look at these guys here. So we have a couple of molecules that have some of these stranger symmetry elements. And just go ahead and confirm for yourself that they have these elements. And you can kind of see what's going on here. These are figures from the book, so you can take a look at the book, you can look at the slides, and try to figure out, try to show these kind of symmetry elements for these molecules. So here we have allene, and then we have phosphorus pentachloride here that has some different kinds of symmetry elements. Now, our focus in the rest of this section is going to be almost exclusively on the water molecule, which is very simple. And we're not going to take too much time trying to parse through these more complicated molecules. That's a topic for inorganic chemistry, and you should take that if you haven't already. It's pretty interesting stuff. So what we can do with these symmetry operators is we can relate them mathematically because we have these different operations, and these will go right along with our other quantum mechanical operators as things that we can do. And there are some points that we can make about what the relationship between these symmetry operators amongst themselves within a point group. So one observation that we have, and these all come from group theory, is that the successive operation of 2 operators is identical to another operator in the group. And so for the example for the water molecule is if we do a C2 rotation, so we rotate 180 degrees, then we follow that by another C2 rotation for a total rotation of 360 degrees, that's equal to doing nothing to the molecule. And this is true, obviously, for rotations, but it's true for anything else. Not that it is equal to doing nothing, but it's equal to something else. And we'll look through some examples of this in class. But if you manipulate the molecule by one of its symmetry operators and follow it up by a second one, you always get a third symmetry operator, or sometimes it could be the same one that you got before, but you get some other symmetry operator that's in the group, because you still haven't changed the molecule by doing 2 symmetry operations, so you have to get another symmetry operator. And this shows us the importance of this symmetry operator E. This kind of observation wouldn't be true if we did not have a symmetry operator E. Some other things that are also kind of obvious that goes along with this is that if you have one sort of operator that manipulates our function in one way, there's an inverse operator that gets it back to unchanged. And this isn't always the same one. In the case of our C2v point group, it is. If you do one mirror reflection, you do that mirror reflection again, you get back to normal, or one rotation, you get to do another rotation. But there can be different operators that return the same function here. The operators are also associative, meaning you can do multiple in a row. So if you can do B and C and then A, or A and B and then C, and you always return the same thing. And all of these points together show us that these symmetry operators commute. And the fact that they commute with each other, and we'll find out later that they also commute with the total energy operator, mean that there's something that we can actually do with these molecules and relate them to quantum mechanics. An important thing for figuring out the symmetry operators for each group is for each molecule is to figure out what group it belongs to. And once we know what group a molecule belongs to, we can, group it with all of its other molecules that follow that same group, and they all have the same types of symmetry, they form the same types of MO, and so forth. So for water, we can figure out what point group water is in. And the way that you do this is by following a flow chart like this one. And so we come up to the beginning and we want to say, well, what is water? Is water a linear molecule? It is not. So we go, no, it's not a linear molecule. And then we say, does it have a CN axis? So does it have a rotation axis that leaves the molecule unchanged? And of course it does. We already found that one. So we say yes, and we come down here. Does it have more than one rotation axis? Water does not. It only has the one. It doesn't have a mirror plane. It does. Does it have the CN axis in the mirror plane? So the mirror plane reflects one of the molecules in half, and that's also the same axis as that rotation axis. So we say, yes, it does. And then we end up at a point group, and it's the CNV. And for water, it's the C2v point group because the CN axis is 2. And so you can follow through any molecule and figure out what point group it belongs to. And we'll see through the next couple of lectures that if you know what point group a molecule belongs to, you can check out its character table and figure out the kind of symmetry that that molecule will have. Now, this can be pretty complicated, so we'll do some examples on the homework problem for class today, but our focus won't really be on figuring out the point groups for molecules. It's a good skill to be able to have, but it is in some level challenging, especially if you have complicated molecules. So here are some examples of possible point groups. And you can go through and follow along. I'd recommend doing some of this. And again, this will be on the homework. So you can follow along with some of these problems on the homework and figure out what point group that these molecules belong to based on their shape. Here we can see some of the symmetry operations for the C2v point group that water is in, and also the C3v point group, which is very similar that molecules like ammonia are in. And let's talk about some differences between these molecules. So we already looked at water. Water has these 2 mirror planes, and it has a rotation axis that's in the same plane as one of its mirror planes. Now, ammonia has 3 mirror planes. It has a rotation axis, but it can actually do 2 different rotations. So what this means is that the ammonia point group has 6 symmetry operations, while water has 4. And I've written this in an interesting way. Here I've written that these mirror planes are different. So I have a sigma v and a sigma v prime, but over here for ammonia, I have 3 sigma v. Now, did I just get lazy? And I didn't just get lazy, actually. What we're saying here is that there's something different about these mirror planes. So for example, if we look at ammonia, I have 3 mirror planes that bisect each nitrogen-hydrogen bond there. Now, if I do a rotation operation on this molecule, I have converted all of my mirror planes into different ones. So if I rotate this molecule by 120 degrees, now my mirror planes, so my sigma v2 here has become my sigma v3 upon that 120 degree rotation. That is not the case for the water molecule. So if I do my rotation, my C2 rotation, my sigma v prime and my sigma v mirror planes are still different. I can't interconvert them. They're reflecting 2 different types of symmetry. One through the molecule, and then one cutting the whole molecule in half. So they are actually different symmetry elements. Whereas for ammonia, they are all interconvertible. And the same is true for the rotation axes. So it's possible to have 2 different types of mirror planes. It's possible to have 2 different types of rotation axes. And it takes a little bit of understanding what the molecule is doing to actually parse through this and figure out what we're talking about here. The last thing I want to do for this lecture is to look at the water molecule and figure out what actually happens to the molecule upon doing any sort of symmetry operation. And we'll start by considering what happens to the identity operator. So what we'll note is, of course, if we do nothing to the molecule, we don't change the molecule. So if we pick a point, say right here in this hydrogen atom, in terms of x, y, and z coordinates, if we do nothing to the molecule, we do not change the x, y, and z coordinates. Now, what happens if we do the C2 rotation? Well, if we do a C2 rotation, we're rotating it at 180 degrees along this axis. So this point that was here will rotate all the way around, and now it will be facing on the other side of this hydrogen atom pointing. So if I have a point that comes out, it's going to be now pointing into the screen. And so what does that do? Well, it started over here and ended over here. So it changes the y-axis. So the point that was at positive y is now at negative y. But it also flips the x-axis as well, because the point that was on this side of the molecule is now on the other face of the molecule. And the z is unchanged in this operation. So if we had this kind of matrix here, doing the C2 operation would take x, y, z to negative x, negative y, z. And that's what happens to a single point x, y, and z when we do this operation to it. We can do the same thing for our mirror plane. So if we look at the sigma v mirror plane, and here we do have to be careful about the designations. If we change to prime, we're going to get different answers. So the sigma v mirror plane is defined as cutting this molecule in half this way. When I reflect it across, now if I started here, I would reflect over here without changing the x-axis, but I would still change the y-axis. So my sigma v mirror plane, it goes from xyz to x negative yz. And the sigma v prime mirror plane that cuts this in half would reflect me from here and then to the other side of this molecule. So it would leave y alone while changing x. So my sigma prime v would be xyz to negative xyz. And we can do this with any symmetry operators. We're going to stick to the C2v point group because it's pretty simple, and also water is one of the most important molecules. But we can see what happens when we do these symmetry operations here. Now, what we can do with this is actually, it turns out that we can construct matrices that describe this change. So for example, let's look at this E matrix where I have 1, 0, 0, 0, 1, 0, 0, 0, 1. What I'm going to do is multiply my vector xyz up against this matrix here. And then what do I get? We'll have to dig back and remember how to do matrix multiplication. And we'll do some of this in class. But when we do matrix multiplication, we take our whole matrix and multiply it by this row, and that goes in the first column. Then we take our matrix multiplied by the second row, and that goes to the second entry, and then our matrix multiplied by the third one, and that's our third entry. So if we do that, we get x times 1 plus y times 0 plus z times 0 is equal to x. And then in the second entry, we get y, and the third entry, we get z. And we can see that this matrix converts our xyz into xyz. These other matrices do accomplish their conversion. So if we go to the sigma v operator, this converts xyz into x negative y z, which is what should happen upon this operation. So we can use these matrices to kind of understand what's happening to a point. And then what we can do is actually multiply these matrices together and get our various point groups. So if we take this matrix here and multiply it by this matrix here, again, we can go through the same process, but what we get is 1 times -1 is -1, then we get 1 times -1 is -1, 1 times 1 is 1. And so if we do an E followed by a C2, that's the same thing as doing C2. And we can do this for any of our combinations here. And what we end up seeing is that we always get a different operator, which is one of the things that we said was true for these symmetry elements in point groups. And so we can see if we do 2 rotations, we end up back at the identity operator. Same thing if we do 2 mirror reflections and so forth. So this kind of table that we have here is our first example of a representation. This table represents all the information about the symmetry point groups. Starting in the next lecture, we're going to look at character tables, which is a much more condensed example of this kind of representation. And we'll see how that contains all of the information that our representations need to talk about all the symmetry. And so I'll stop there, and we're going to go through a lot of examples and get our hands dirty, actually, looking at molecules, flipping them around and so forth in class. So if you have trouble conceptualizing this from a purely, video lecture, I don't blame you. And we're going to spend a lot of time working on this in class.